All right. Well, good morning or good afternoon or good evening to everyone. This is a web-based presentation today, so you could conceivably be anywhere on the planet. Um, but thank you for attending today. My name's Jason Titcomb. I'm with LMGI. We're up in Portland, Maine. We love uh, selling Siemens CAD, CAM, and analysis software, providing solutions and training for that software. It's what we do. It's what we love. Today we're going to have a short presentation using Siemens NX platform, and we're going to talk about programming your CMM inspection machines, coordinate measuring machines, and so NX is I guess you would call it a CAX, X being kind of a variable, right? You've probably seen that term. You got CAD for computer aided design, so CAM for computer aided manufacturing. And so NX is kind of a platform that some of the biggest manufacturing and engineering companies on the planet use to design and test and validate their products. And CMM programming is just another one of those things. So you can actually buy NX for just CMM programming. Ideally, it would be your platform of choice. So if you do your design using NX CAD, that's awesome. And I'll show you a little bit how you'll benefit from that. And then if you use it for your machining, you'll be able to utilize a lot of the intelligence that you could put in while the CAD designer is doing his work to almost give the machining guy some hints or some extra information that would help him do his job. And the same goes for CMM. You can, as a designer, you can kind of at one step put all the information in required to create that digital twin of your design, and then it's consumed in all the other areas of your NX platform. And also having, one unified system that everyone in the company is using. You have a common interface, so you're not having to jump to a different piece of software and kind of relearn it a little bit. You stay in your NX platform. If you move from a design mode to a manufacturing mode or an inspection mode or an analysis mode, you're all within that one NX platform. So that's really the sweet spot if you if you choose to use NX for your complete enterprise. That's wonderful. But you can use it for its individual capabilities as well. So today we're going to, as I said, we're going to talk about kind of the CMM inspection programming and what the benefits might be. So why would you want to do it? Typically, I guess if you were a really small shop, it's nice to be able to do it and identify collisions and make sure your setup is correct before you actually give the job to your inspector. Or larger companies, mid to larger size companies, may have quite a heavy workload on their inspection equipment, and they don't want the inspector to have to take time to set that up and make sure everything's right before he actually starts measuring parts. You want to just get him measuring and checking parts right off the bat. Kind of like machining. You don't want the guy out there pushing buttons at the machine tool. You want him to push one button, the cycle start, and when it's done, take the part off, ideally, so that machine's making money for you. But then the other piece that is kind of nice, you want to be able to get information back from the CMM, the inspection results. On a milling machine or a turning machine, the result is the part comes off. Well, an inspection machine, you get the actual results. Is the part good? Other features within tolerance, things like that. And NX has that capability to give you that full loop. There are a number of major manufacturers that NX is supporting with full kinematics machine kits, meaning that the models move around with the same acceleration and deceleration. It knows the mass of the machine, how fast it can move around, its limits of motion, so that if you're trying to measure a part that's too big for that machine, you're gonna know it before you go too far, rather than setting it up on the machine and saying, oh crap, I should have put this on my other CMM machine. I thought it was going to fit. So, and then there's a number of probing systems. When I first started learning about this, I was a little surprised that there were so many variations, different combinations of manufacturers, and then certain probes that they offer. The probes can articulate around at different angles as needed. It's pretty amazing technology. So, without reading the slide, you'll see that there are a number of machines and probing systems that are supported. So starting with your design, and we'll show you this in the demonstration, a really powerful aspect is if you create your digital specification in the CAD 3D environment, you can put all your annotations that you would normally think of as being in the draft environment. You create these in this is kind of the new trend. I remember there were days when people thought that I'm just going to draw in 2D, that's good enough. It's good enough for us. We don't need 3D. And then little by little, people started realizing, wow, this 3D stuff, this has got a lot of opportunity. This has got a lot of benefits, clash detection, mass calculations, things. All this it goes on and on. So now people are starting to realize that these old, the flat drawing is not such a great way to convey the design intent to the downstream people that have to make and inspect the components. So they're now using this PMI, product manufacturing information, which allows at the front end, you can create the specifications right in the CAD file, and they become attached to faces that are identified. You see in the picture here that when you touch one, it identifies the actual physical characteristic on the geometry, and that's another benefit of having that in the 3D environment. Not to mention, you can just rotate the model around to better understand what the characteristic is that you're going to machine or measure. And so that's a great benefit over two-dimensional drawings. But we still have to use these 2D drawings. It'll probably be a good long time before they go away completely. So NX also has the ability to just grab these 2D, these PMI annotations and bring them into 2D with very, very little work. So reusing all that work that was done. And then I'll show you here in the demonstration very quickly that the link to PMI functionality is a link. It's pretty important to think about that word link. So if you realize there was a problem with your design and you need to tighten up a flatness or a true position tolerance, you go back to the design component, the digital twin, you make a change to that feature control frame that says how parallel or concentric or whatever that characteristic has to be. And that actually trickles down to all your other, it trickles down to your 2D drawing, it'll go down to your CAM system, and it will go down into your CMM system. So you don't have to you don't have to remember to go change it in your CMM, and you don't have to remember to go change it in your CAD. It does what computers are good at doing. It just automatically does it for you, and then you just kind of look at it and say, yeah, that looks good, save the file or re-release the file, whatever. So it's all linked together, which is really nice. So the software can also, in the CMM environment, kind of automatically create these paths based on predefined methods of inspection, which you can alter yourself for your best practices. So that is another very powerful. This is kind of a lot going on in this slide. I guess it'll make more sense when I do a couple of demos. I have 3 basic demonstrations today. So here you can see it starts with the CAD, and it will flow down into your creating your inspection program. To get that inspection method, you might say, or how you want to touch the part over to the machine, there's different ways. There's this DMIS format is a little bit like a G-code format. It's kind of a generic industry format, and you'll see that NX supports a couple different standards. I love standards. The great thing about standards is there's so many of them, right? But they do support this, and you can tweak that if you want to. And there's also a direct API connection to many of the machines that NX also supports. But at any rate, you send off that information to the actual machine, and then it will give you the results back. And I'm going to show you that also in the demonstrations. And then you can see if that part is within tolerance, within spec. So with that, I'll go do a little bit of a demonstration here. I'm going to start out and just kind of show you kind of good, better, best, I think, workflow. I've just got a simple little part here. I don't actually even know what it is, some kind of a Nikon. It's an Nikon cap lock, of course. So it's just a very simple, it's a body, so it probably might have been designed in another system. It has no PMI on it, which is okay. So this is kind of going to be your worst case scenario if you was designed in maybe some other, or this is a part that the customer just gave you and you had to machine it and then inspect it. So you didn't design it. So the process is to choose new, and it's going to use a template-based system, which is great because you can tweak these templates over time for your best practices. In this case, I'm going to grab this Wenzel, but you can see there's a number of machines delivered here. And all this is kind of like a higher level file that has a bunch of information all ready to go. In this case, it's all CMM information, and it has some predefined things like tools. So the tool rack has, this has a very small tool rack. It has a tool changer, which is pretty cool. So you can grab different styluses or probes. And so that kind of all comes in. We'll talk about that more. But first, let's at least get the part positioned. You just select the component. You can certainly use assembly constraints if you want. In this case, I'm just going to move it up so it's not buried inside the granite. And so from here, you'll see you'll have an inspection navigator tab. And NX is pretty intuitive. You have your assemblies. If you're in modeling, you'll have your part modeling navigator tab. If you're in manufacturing, you'd have a manufacturing tab. In this case, we're in inspection, so we have the inspection navigator tab. And then once you're on that tab, you can kind of look at the information in different ways. So this is the entire inspection program right here. They make it really easy for you. They categorize things into folders so that you can get the output that you want. We'll cover most of these, I think. So part alignment is kind of a bare minimum. Just to get something to show up on the screen that's not totally crazy, I need to give it some kind of direction as to which way is up. In the real world, you'd probably have a specialized routine that, see, the CMM doesn't really know how that part is aligned. And what people would do, you might just drop it on the table and put a clamp on it. So the magic of a CMM is that it can reorient its coordinate system internally, so the part doesn't have to be perfectly set on that piece of granite. I mean, the middle of these machines could just be raw steel without even being granite, technically, because it can realign itself internally, mathematically. So you can use this alignment assistant, actually, if you wanted to, and there's or you can just create your geometry yourself and say that is just going to establish the part orientation. It's not actually going to measure anything and test it for whether it's a valid. It's just simply establishing the orientation. So there is a wizard in there to kind of automatically create that stuff if you want. You see it creates all the necessary alignment. There's a plane and a path to touch the plane, and there's the cylinders and then the paths to touch the cylinders. This probably looks a little complicated if you're not familiar with other software that does this kind of thing, but there is there is a wizard to automatically help with that quite a bit. And the reason these all have no's is as you create things, very much like CAM, at some point you generate, it kind of just recalculates, it generates the path so the motions are proper and things like that. That's why we have those red no's. They don't do it all the time because it is a little bit of it takes a little bit of time, just a few seconds to do that, and they don't want to bog down the user experience, to constantly delay that. So you have to just, at some point before you're done, just generate. Now, let's see. So I did my teach point. So if I had to manually create some areas to inspect, you would just come up here and say, okay, I want to define a face, and I'm going to just middle mouse, and we hit this one and middle mouse, and this one middle mouse. So just as an example, there's 3 features, and maybe I'll say, okay, at one point I'm going to need to measure some cylinders, so I'll just do like this cylinder. Just double, I don't think I even need to flip that, but I'll just do it anyway. So I've got 3 planes and a cylinder so these are kind of like characteristics on the part. And then you can certainly just click one of them and then create your inspection path. And you'll see it kind of defaults to this method. So, and you can choose the probe, or there's even ways that the software can automatically choose the probe for you. And then you would say create a sub operation. So now you're starting to see the moves, and you can do this. This is all coming from the method. So again, you can certainly change it here, but kind of like if you get sick of changing it all the time, you go to your method and then you change your best practice so that now every time going forward, you're going to have your preferred way of measuring these flat planar characteristics on the model. Sensor, the word sensor is kind of a combination of a probe and a direction. Don't really need to get into it. You can have it, if you want to give it an angle specifically, and you want to say, I want this sensor to be tipped at 90 degrees in the A and 45 in the B, and that's the direction I want to come in, because you might have a really complex part. You need to kind of sneak it down in a certain area and touch a little tiny face in there. You certainly have that control, but I just want to keep things simple. And so that kind of creates the moves. And then if you want, you can do a quick replay. The benefit of replay is it's probably a little faster. The machine doesn't actually move around, so you don't have to wait for the machine kinematics to come on, kind of move into the scene. But later I'll show you the full machine simulation. So that kind of gives you a nice quick preview there. So you can certainly do that, and that created my inspection path. But there's also a very fast way where you can do multiples. And if I grab a bunch of these, there's multi-feature paths, and it's already kind of grabbed those because I pre-selected them. It will automatically choose the tool if I want to, based on some strategies. And as far as this, I'll just let it rip and you'll kind of see the benefit, and hit OK. So you can see it actually created my paths for me based on those methods. So the methods are over here in this view. So there are, as I said, there are a number delivered that just came across with the template, but you can adjust them. So if we looked at the plane and the cylinder, you see there are my things I just created underneath that method. So if I want to change the method, I can change it in one place and it will change everywhere. So it's a really powerful concept, the way they use these methods. If you're familiar with NXCAM, you're totally familiar with the concept of the method. The method is like, it's a container for the information for how you cut the part. And in this case, they're a container for the information on how you probe the part. And they're a great way to reuse or set and forget that information. Let's see, so that's multi-part. I'm looking at my little notes here. And then in order to say whether the part is good or bad, you need to have a tolerance. And here we could make maybe a flatness tolerance here. And I think I just need to select a feature and hit OK. So that just makes the tolerance. I probably went a little too quick. I probably should give it like 0.1 for flatness. Um, so again, this is the manual way. It's a little steppy. You have to kind of tell it if there's no PMI information, it doesn't know what your flatness requirement is, and you have to tell it. And there's ways in this dialogue to do that. And you can also template these if you were to work in a totally manual method. You could certainly template those out. So again, this is kind of worst case scenario that I'm showing you here. And so I'll go generate that. And then to get the code, once you're all happy and you have enough paths, you just post-process that. And in this case, I'll grab the DMIS52 and just hit OK. And if you're not familiar with this, this probably makes your head hurt to look at it. But this is a language that is used to drive the machines. And you could see, like at the end, there's my I think that T represents a tolerance, and there's my 0.1. And you could see there's a measure, so we're doing a measure plane, and there's all the touch points, and so it's not too bad. Some people write these things by hand, believe it or not. So I think that's pretty good for the first. I'm going to do close all those parts, and the next up is probably your better scenario. Oh, I hate that when that happens. Give me a second. User error. Where did the software go? Okay, so the next part is got a lot more done to it. So this was a part that you may have designed yourself. And if we look into it, there's these so-called model views, which are great. Other CAD and systems have these model views like Solid Edge. We also sell Solid Edge. And you can do your PMI, product manufacturing information there. So these model views, if you were to go paperless with no drawings, this is what you would be seeing if you were on the floor measuring, or if you were a machinist. You'd be able to open this up and see all the characteristics without having to use a flat piece of paper. So the model views are kind of, they represent the sheets or the views that you would typically have in a paper drawing. So from just to kind of give you a sense for how you can now reuse this information, certainly CMM is one of them, but if we do File, New, Drawing, hit OK, and I'm just going to close that to go to the next step. Just going to say next. Let's go get the PMI from the model view. Next, PMI top, finish. So you could see that these annotations were created once in the CAD file, and they can be brought in very quickly, and they're totally associative. If you go back to the design model and change this tolerance or this value, this will update in the drawing, and it will update in all of your other downstream processes as well. So now let's go ahead and do a measuring job. So we'll do File, New, Inspection, and I think I'll use Sheffield maybe. Yeah. Once again, this is a template that has a lot of things predefined, like your your probes and maybe some tooling for setup. And you see that all your annotations come right in as well. So again, a little redundant here, but I'm going to do the part alignment. I'm going to do my teach point and just give it at least my minimum point here on this high corner. And that face, that kind of just tells it that's the up. And then because we have all of this information in the form of PMI, there's a great link to PMI, kind of a magic piece of code where they are going to go, and all you need to do is identify the component that has the PMI on it, and then just let it run. And we should see a list of everything it was able to glean off of that component in the way of inspection attributes. So that's great. And then I'll go ahead and generate all this so there's not so much red here. And if you look at the tolerances, notice there's a no still in the tolerance. Well, a couple of them, it's a little unclear. There may not have been whoever made, this is probably like an example of, just to keep it real, okay? Sometimes the guy, when he made the PMIs, they weren't attached in a certain way, or they didn't give it enough information or something like that. So this is a couple of examples where it's missing a little bit of information, and I think it's just a vector that it needs. It tells me in the prompt down there, but again, it's just kind of an example. Vector direction, I think we can just give it something like that. And same with this one. This is a perpendicular, and I think it doesn't know, perpendicular to what. It should be perpendicular to B, but for some reason it wasn't able to get it. So that's okay. But the point here is that they are editable after the fact. It's going to save you tons of time. But the result is things that are editable and after the fact. So that's kind of good. It's not some kind of canned system that you can't ever change after it's created. So those succeed now. So that's pretty good. And then you want to probably simulate the entire process. And I would typically go to the top inspection program, and I would use simulate machine. So I'm going to zoom out a little bit here so we can see a little bit more of the machine. If we look at simulation settings, there's some settings for collision. We definitely want collision check on. And so right now we should be getting, because you can classify things in NX, so we should be getting, it's going to test for collision using these pairs of anything that's classified as a tool and anything that's classified as a part, and then anything that's classified as a tool or a fixture component. So out of the box, we should get those. If any of those two things hit each other, and there's some other settings for that, relate to the simulation. And let's just go ahead and play this. So it's going to grab a probe. You're actually seeing the DEMIS code that so it posts the code out, and then it actually drives the machine with it. I think I didn't have stop on collision, but you see it flashing. Go ahead and hit this collision check for collisions. Forgot where that is. There should be a stop on collision. So I'm just going to let that go. So obviously there's collisions. If I hit stop and if I go to details, it shows you every little collision point right here in this. So you ultimately want this list to be completely empty. So these are pretty gross right there. You could just tell by looking at it, but sometimes it can be a very subtle, and you don't want to break one of those probes or they're kind of expensive. The machine will probably stop before it'll do too much damage. But so how do you deal with that? You could go and insert moves, but there's a great way that software has to kind of automatically find and fix these collisions. There's a couple of great things. So in my inspection paths here, I can right click or there's buttons up here, so I can do collision avoidance, and I can resequence the path. So resequence optimizes for the kind of the shortest, so the machine's not jumping all over the place. Essentially, takes all the paths and comes up with the most. There's really nothing to look at; it just does it, shortest distance. And then collision avoidance. There are a number of output settings here, but one thing you probably almost always want to do is set a nice fat clearance plane here off of this top face. So that's a nice safe as it moves around. There's that. And then you can ask it to do any of these other things. I'm pretty much just going to obviously leave them all on to see, so we can see the most benefit, and it will list the output of what it did when it's done. So this is very cool. It kind of breaks the model up into a bunch of triangles. So it will look at any model kind of generically because of that, and it can automatically create. So it tells me here, make this a little bigger, that there were 5 transition points inserted here. No collisions there, blah, blah. So you see, you get a nice report for starters. And if we, for example, if we look at this path, you see, I'll click and hold, just get my rotate point. You see these extra moves right here. These were added in by the software. I probably should have shown you before and after. And then if we just ran it at this, if we ran it again, we should have collision-free path. But you can also do a resequence path, which will optimize. Now, I'm doing this on purpose. I'm kind of doing it in reverse order. So now let's go and do a simulate machine, and I'll just let that rip. We still might see, oops, sorry, I need to actually simulate the whole program. Simulate machine, and just let that rip. And we might still see the probe kind of clip one little place. It's fixed most of the paths, but I think if I remember right, there's one little spot where it might, right there. And that's just because I optimized the order that things happen. And you can see there still are a few little collisions here, but it's so easy just to right click and do collision avoidance and just run it. So I kind of did it twice so you can see it again. Deliberately did it out of sequence there. But you would kind of optimize first, and then you would run collision avoidance, and it would just do it in 2 easy clicks, which is really really pretty sweet. So you can see, if you have really good PMI in place, you can get an inspection program knocked out in no time. I wouldn't want to say how many minutes, but you judge for yourself. How long does it take to set your part alignment with a teach point and maybe a couple of other phase touches, link to PMI, and then a couple of right clicks to optimize and collision check, and you're just about all ready to go. And maybe we'll do another simulate on that, make sure I got, and I guess it's possible that it might miss one. I would hope it wouldn't but it might, I guess. That's why they have the highly accurate collision avoidance in there. And you could always go back after and adjust. Some parts are really complicated, and it's really tight. So apparently it did its job and there's no collisions there. So that's awesome. And then the last demonstration that I have is kind of showing you the kind of the round trip. File, close. I thought I was going to have to go dig around for that part, but so here's a finished part. So this has already been programmed, and it's already got all its inspection paths. And if we maybe if we jump back to the slides here, go back to this previous page to kind of remind you. So we've gone from the CAD file. We've created our inspection program. We've outputted a DMIS format. We've sent it to the machine. We've measured it. And now we'd like to have that information come back in so that we can somehow convey the results of the inspection. Maybe the part didn't meet spec, and we'd like to contact the customer and ask them if, you know, if by any chance that might be okay, or if and they might evaluate it. So how do you capture, you know, that information? There's a couple of different formats, and again, there is an API that you can have NX talk directly to the machine through a kind of a piece of code that the machine tool builder makes. But let's see. So the first, my little notes here, down in tolerances, I just right-click, and again, there's buttons up here to do this too. Measure data. Right-click. Measure data is how you can go ahead and bring in, I think in this case, because I don't have a CMM here in the office, so I have to go and browse. But there is, so someone provided me a DML, which is the output from the CMM, and I'm going to say I'd like to have it come into this coordinate system. Display some measure points and the original design points where it should have touched, and I can also ask it to display reconstructed features. And you'll see what that means in a second. And the deviation needles would come into play if you would do in a probing, like an impeller, where the probe actually drags along to measure a contour. You can get these deviation needles that can show you the deviation, so there'll be like little spikes or whiskers. None of the type of measurements we did support that, but that's what the needles are about. And then the scale of the needles are, you know, it's kind of high. It exaggerates, it helps you visualize the deviation in the path. So the machinist might look at that and say, oh, I see what's going on because of the way I've got my end mill coming around, that it's deflecting a little bit. Let's try a shorter end mill or something like that. So you can see it brought in 240 points. And if I expand out, here's where the magic. So most of these characteristics are good. Some of these are out of tolerance, and it tells me the deviation and it flags them nicely here. If we zoom in a little bit, so that red is that reconstructed. So this was a plane. So that was the type of characteristic. So it's kind of reconstructed to show you that plane, and you see the points, and it's actually got, it's a little hard to see unless we go to maybe a static wireframe. That kind of helps a little bit. I can actually go and turn that that constructed I think that's the one. And then when I touch this, we can kind of just see the points, and you can kind of see the ones that are. This would be nice for the manufacturing guy, I would think. He might see that and think about how he's clamping this part in the machining process, and it might really help him understand why that face is not flat as it should be. And again, there's a cylinder, and it's showing you the points and the deviation here. So all really valuable information. What else can you do here? You can right-click and you can inspection analyze. I'll just turn all this stuff on, but basically this will give you a kind of a raw a raw text format. You'd actually say list output, so I don't have to open the file. But, and this, what do you do with this? Well, I don't know. You could possibly, because it's a nice raw format, you could possibly consume this in some of other software. You may have some statistical process control system or something that, who knows, but it's kind of a nice raw dump of the data. And you can also do graphical reporting, which is pretty cool. So if you needed to kind of convey this information to the customer, let's see, there's a graphic report, and I might use, let's see, we could get the point data from, let's do feature control, the cylinder, feature control frame 31, and there's all the point data. So let's say you want to have really granular feedback on every point, you can get that. Or if you wanted to do tolerances, you could do that as well. And it's going to tell me, so I'll give this a name. And just hit, obviously you can set the camera, you can have a static wireframe or shaded view, what have you. Go ahead and hit OK. And now we have our report. And you can bring that back up at any time. And then you can create a PDF of that if you want to output graphical report. It's just telling me, hey, make sure you have a nice clean view. Actually, I did one before. If I open that up, we should be able to see one that I did before. So yeah, great way to capture your inspection results and get a conversation started with the end customer. It's a nice way to digitally capture what happened, not just this conversation over the phone, right? Where he said, she said. It's a great way to capture that. So there's a few slides here that we can kind of, mostly just informational. It's kind of good because there's different systems that are supported. Just some, you would probably, if you had one of these machines and you saw the slide, this would be very interesting to you. So like which probing systems are supported. So mostly these are for reference. See this Mitutoyo, this I++ it's an API. I guess that's probably just noise to you, but it's application programmer's interface is typically what API means. But it's basically a black box that it's a generic way that, in theory, you can talk to any machine. So on one side is the machine tool builder, but then on the other side is this common language that you can say, go touch something, or then ask for results. So it's kind of a, kind of a Rosetta Stone, or it's a way to communicate to the machine without having a text file. So it's a direct connection, and it's a little piece of software. Other than using, one of these DMIS, which are obviously just text files, kind of like G-code that you can send off to the machine. So that's pretty much wrapping it up. Hopefully that gives you a good overview. If you have interest in CMM inspection programming with NX, feel free to give us a call here at LMGI up in South Portland, Maine. And sure, they're mentioning here that there's some great training material that they provide to go with this. I actually used the training material, a lot of the components from that material. It's really good. And then there's a large CMM library that comes with or is available. Some of them are delivered right when you install the software, and then some are downloadable. I never knew there were so many CMMs out there. It's crazy. So thank you for your time today, and everybody have a great afternoon, and we'll see you next time.